Now we are in this video going to understand what are the clock features in NXP S32K144 microcontroller and what are the different clock sources and how to configure it. Okay, so now starting with the clock peripheral in our NXP S32K144 microcontroller. So this is the reference manual which you can also find from the NXP website, or I will upload its link on the below description link, and you can download it from here. And under the chapter 27 is the one where you can get to know about the clock peripheral and the clock block diagram of this microcontroller. So maybe for some people the data sheet reading is quite tiresome and boring, so you can refer to the blog on the Gettobyte website, which I have written on clock peripheral on K144 MCU, in which I have told about its in a bit engaging and using the graphics. So let's just understand it from here only, that in a clock peripheral in NXP to K144 microcontroller, basically there are three modules. Okay, first is system clock generator, then is low power oscillator, and the peripheral clock control. Now, out of these three clock sources, three clock modules, the one which are would be of primary concern of right now would be a system clock generator and the peripheral clock control. So, system clock generator, as its name says, system clock generator. The microcontroller's clock is being generating using this module. So, this module is the one which would be having the four clock sources. External crystal oscillator, either we are using fast internal oscillator, slow internal oscillator, or the system phase lock loop. So out of all these three four sources, we can configure which clock source to use and correspondingly generate the core system clock of the microcontroller, and this part lies into the system clock generator. And after configuring the core clock frequency, our peripherals would be getting the frequency for so as to configure their clock frequency. Okay, so you can read about this from my blog also. You will be getting much better idea and clarity also. Okay, now in a clock there are many other things also which can be read off. So you can refer to the reference manual of the microcontroller for any queries or doubts. You can mention them in the below comment section. Right now I have told you about the basic introduction and basic idea of the clock peripheral in the this microcontroller. Now we are going to move forward on how to configure this clock peripheral for the S32K144 microcontroller. So for configuring the clock peripheral in a microcontroller, we would be using S32 Design Studio IDE, as I have told in my previous videos. Okay, so there are there are code configuration tools in our S32 Design Studio IE, via which we can, via using the GUI interface, configure the clock, which clock do we need to use, what frequencies at which you need to use, and what all things. So now let's just navigate and understand about those things on using the Studio Design Studio IDE. Now for understanding about the clock peripheral and how to configure it, I am going to use the Hello World example of the S32K144 MCU on the S32 Design Studio IDE. So as to use this and how I have installed and opened it, you can refer to my previous video on getting started with S32 Design Studio IDE part 2 and the part 3. Okay, so now if we go to the selecting on this project, and if you navigate to the clock view of a code configuration tool, so you will be able to see there are number of views, number of windows via which we can configure and see about the clock peripheral of a corresponding microcontroller project that we have opened in Studio Design Studio IDE. So as we have opened for our this S32K144 MCU. So over here you can see that there are wait, let me just minimize these windows. Okay, so this is the whole clock diagram, clock tree of our S32K144 microcontroller, and this is the main system clock. Select system clock SCG module, system clock generator, which I am talking about is the most important one, and via which all our core clock frequencies, system clock frequencies, and all the clocks are being configured, and via these clocks only then our peripheral clock are getting the input. As you can see over here, SOC divided one, SPLL, SIRL, all these buses, these are all the different buses. Okay, so these are buses, these buses are being configured over here in the SCG module over. Okay, So, and as I have told you, there are three clock sources, four clock sources basically: FIRC, SIRC, the fast internal oscillator, slow internal oscillator, crystal oscillator, external crystal oscillator. If we are using, so we need to connect those on the EXTAL and XTAL pins of the microcontroller, and then the SPLL. So this is the mux which would be you kind of which we are depicting, okay, for understanding in the GUI. And we can configure it via which clock source we need to power the system clock: fast internal, slow internal, SPLL, or the system clock oscillator. If we are using system clock oscillator, so our system clock oscillator would be configured in these things, okay. So let's just now make this the default configurations. So yeah, this is the clock diagram where which, and over here you can see we can configure for the each peripheral which clock source we need, which clock bus we need to use, and then correspondingly configure those clock buses according to the our need. So now in this video there are many things as I have told in the clock, so we'll be doing things one by one. So in this, I would be just only focusing on SAG. I would be configuring SAG at using the crystal oscillator 16 megahertz, and then configuring our core clock and system clock as 32 megahertz. So I'm going to tell you how we'll be doing it and how to do that, so that you get an idea. Then for the peripheral clock configuration and enablement, we'll be understanding that thing when we'll be configuring the other peripherals. So step by step doing all the things. This video is on clock peripheral, so understanding the main module of a clock peripheral, that is SCG, system clock generator. Okay, so now let's just configure this via this GUI that using the crystal oscillator of 16 megahertz, and then configuring our system clock and core clock as 16 megahertz using SPLL as a clock source. Okay, so now we are using the crystal oscillator as I have told you, with configuring for the 16 megahertz. As on the electronics development board that we are using, it has onboard crystal oscillator of 16 megahertz. Okay, now so yeah, typing over here the 16 and then click enter. Okay, so now as you click enter, you can see there are red boxes being done. So it shows that, okay, like if you hover over them, you can also see the error that output frequency must be in range of 180 to 320 megahertz. But right now, after configuring our SOSC at 16 megahertz, our output frequency has become a 448 megahertz. You can see over here. So now we need to configure the dividers and multiplexers of the clock SPLL, so that we can reduce this thing. Okay, so I am going to make this divide by 2, multiply by 2, and then divide by 24. Okay, so in short, dividing by 14. So now after that it has become 192 megahertz, and then you can see, okay, the red box has gone. So this is very helpful and easy way for configuring the clock. Okay, you can just configure the clock. If you are doing anything wrong, corresponding boxes would be becoming red, and it would be hovering over them. You can see what error you are making. Okay, and now we need to configure this like the system clock using the SPLL. Right now it is via the FIRC, that is 48 megahertz, and that is what being fed to our core clock is 48 megahertz. So now double click on it, and you can we will select the SPLL clock. Now again it has become red. Why? Because if you hover on it for it, so it shows at maximum frequencies of 80 megahertz in run mode. So there are different run mode, different kinds of modes on which you can run this microcontroller. I would be coming on different types of modes and power mode management of this microcontroller in separate video. Right now I am just telling you that there are two modes: run mode and HS run mode. Okay, so in the run mode, are the frequency that can be output from this multiplexer can't be maximum, can't be more than 80 megahertz. Okay, in run mode. So we need to divide this via again some divider. So clicking on it, and let's divide it by 16. So you can see our core clock and system clock has now become of 16 megahertz, and all the red boxes has gone. Same way out over for the HS run mode also we are going to do. Okay, so yeah. Okay, so in the HS1 mode, also that's like the we have configured SPLL and dividing it by one, and no red boxes are coming. So now clicking on the update code button, we can update the code. Now the what all configuration we have overdone here, corresponding impact, corresponding code would be changed. Okay. So but you can see over here there is a problem showing on the clock. Okay, error, problem in code generation. The ratio of frequency between HS run mode and run mode for system clock must be less than or equal to 3. So it is showing that our core clock frequency in HS run mode and in run mode it should be less than 3 on dividing them, but it is right now more than it. In run mode we have 16 megahertz and in HS run mode we have 96 megahertz. So we need to make this division value ratio of these two less than 3. Now, so like you can see over, if we are doing any configuration, if we are doing any wrong configurations, corresponding red boxes or corresponding errors you will be able to see. So these are some of the features of the Design Studio ID, and using the NXP32K144 for microcontroller, we can get to know about. We can get to know about, okay, there are many things to be taken care of, many types of clock, many types of multiplexer dividers, and things that need to be taken care of. So in our HS run mode, let's just divide this dev core by the 3 so that it will become come at 32 megahertz. Okay, and now in our HS run mode and run mode, it is 32 divided by 16, that is 2. So now you can see there is no error showing over here. So yeah, now on clicking on OK, our code would be generated. And when we have clicked on OK, you can see there are corresponding files that are being shown to us. Okay, clockconfig.c and clockconfig.h. Right now it is updating code. So yeah, clockconfig.c and .h. So these are the two code configuration generated files which would be having the input values that we have configured corresponding to it. So is to understand this part, you can refer to the blog. Okay, in the blog I have told very in a proper step by step way, and what are the different source files, what are the different SDK files of the clock, and how does the clock configuration is being impacted on configuring the things. So like you can see over here, as when we have configured the SOC as 8 megahertz, so there are the structure in our code is being you can see over here frequency is 8,000 hertz. Okay, 8 lakh hertz basically. And when we have done it for 16 megahertz, correspondingly our code is being changed, and these files are being generated automatically in the clock config.c and .h. So it's like actually without writing any code, we have configured our controller, and we have configured the code, the peripheral of a microcontroller. So to understand about this clock, the code structure and the different file structures of this, you can definitely check out my blog. Overhead I have told things in a very detailed way and in a very interesting and a systematic way. Okay, so now let's just go to the demo code. Now what would be our objective is, whatever clock configuration that we have done over here, okay, in our code configuration tool, now we would be seeing what all clock values are there. We would be seeing that yes, over here the example which I have written, what are the different clock frequencies of different clock sources, like system clock, FIRC clock, SIRC clock, SPLL clock, and the core clock. So we can see, okay, what all configurations we have done and what we are getting as output. Okay, so yeah, so this is the demo code. This is the demo code which I have built over the Hello World example only. So over here there are two APIs which are important to be used for the clock peripheral. Okay, so in the SDK folder structure, under platform and under drivers, you will be able to see there is a clock for structure K1XS and the STD2 clock K1XS.c and .h. So these are the two important files, HAL files, that whose functions would be using throughout our main.c in the application code building. Now, so as to understand about this clock, different SDK files, different .c .h files in the driver files of the clock, you can check out the blog. Over here, I have told in a proper tree structure way and in a very simple way. Basically, there are four files that would be our focus when using clock peripheral. Okay, so in the SDK of the clock of the S32K144 that we have downloaded, so there are these four files, clock config.c and .h, that would be automatically generated corresponding to the values that we have configured in our design in a code configuration tool. So that you can see over here, clock config.c and .x. So in the .c there is all these structures being initialized. Okay, so there are structures, and in the structures there are further structure names, and the using the proper C programming structure concepts and those things, you will be able to see. Okay, so whatever the structure name is, FIRC config. So what are their values? What are their divider values, and what are their multiplexers? What do you values? The crystal oscillator we are using. So what is the frequency that we have? The which frequency we have the connected the crystal oscillator and these things. So on the clock config.c and .s, these will be automatically generated via the code configuration tool, and the clock underscore S32K1 and .h, these would be having all the functions that we would be using in a main.c and application code for using the clock peripheral. Like the clock system initialize, this function would be used in a main.c for initializing the clock. You can see over here. So this is the clock drive initialize, which would be configure clocks for the port, for all the ports and for all the peripherals that we are using. Okay, and yes, so you can get to know about these which APIs, which API to use, how to use, and those things in a blog, and that would be very helpful for you. Now let's just focus on this demo code that I have developed. So in the demo code, what we have basically done is, as I am telling you, that we have written a code using the hello world example. Over it we have only built it, and we have inserted this code. We have basically created the six variables of clock bus, core clock, clock source, okay, SPLL, FIRC, SOSC, and SIRC. And all these I am get used. These variables would be used in this function clock system get frequency. So this function, what will it do? It will just tell us, okay, we just need to tell the that which clock for which clock we need to get the frequency and the variable to store that frequency. Okay, and it would be getting then in the filling this variable with whatever clock frequency that clock has been correspondingly configured and has been initialized with. Okay, so like this is the code which now let's just compile. Okay, I will be also uploaded this code on the GitHub, so that you will be having an idea and get to know about it, and take it from there. So let's just first of all build the code, and I have connected the hardware with me, and now we'll be just debugging it and seeing these values on our debug watch window. So now as you can see on the screen of mine that I have connected the hardware, okay, and I have connected the electronics version 2 development board, which is having an S32K144 microcontroller using the J-Link V9 debugger. And this is the code which you can see over my screen. So now we are just going to debug it. So as to see how to debug it and how to do the things, you can refer to my previous videos, okay, on the getting started with design studio part 3, in which I have told about the debug configurations and the build configurations, and you can also correspondingly see the blogs on the Gettobyte website. So as we are using J-Link V9 debugger, so we will be using the J-Link debugging GDB server and Hello World S32K144 for debug flash. Okay, J-Link. So now let's just debug on it, and now it will be connecting with the J-Link, communicating with the J-Link V9 debugger first of all, and then it would be asking for switching to the debug perspective. Okay, so it has now switched to the debug perspective, and you can see over here there is a debug view in which it is showing that which file it is stopped at, which function it is stopped at, which line number it is stopped at, and the address. And over here you can see the main.c, and there's this small blue pointer that debug current instruction pointer is over at this line in this file. So these are all these some features which becomes very easy for us for when we are developing the code on microcontroller. At first it might become very confusing, and lots of things you can see on the id, but you use 2 to 3 times, you will be getting very much familiar, and find it very easy to use. Okay, so now what we are going to do is we are going to run this code. Okay, and there is a view which I want to show you, expressions view. Okay, expressions, sorry, expression view, expression. Yeah, okay. So in the expression view of the debug, when we are doing debug, we can like add the global variables, global structures, or the global all the global variables over here, and we can see their values in the runtime. Okay, so yeah, so I have copied over here all the variables that I have created: frequency bus clock, core clock, clock output, and then the SPLL clock, SIRC, FIRC clock, and SOSC. So clock output and these things. So now let's just run the code, and you will be able to see here when we stop that first of all my LED is blinking on the screen. You can see over here it's blinking from blue red, so it means our code is running fine. Let's just stop the code, and you will be able to see that all these variables are being filled with some values, and these values are those values only that we have configured in the code configuration tool of the clock. So SOSC is 16,000 megahertz, 16 megahertz, SPRL is 96 megahertz that we have configured. Our core clock and bus clock both are being configured, both are generated of 16 hertz, that is 16 megahertz. Okay, and these things. So yeah, so using this demo code you can get to know about the different clock frequencies that you have configured for the different clock sources in the SCG module. Okay, and now these clock sources would only be used for a peripheral clock. So that's it in this video. I just want to demonstrate how to use the clock peripheral, how to configure them on the code configuration tool, and how to build and debug the project for that. So much more in details you can get to know from the blog also, in which I have told various things about its SDK files, its APIs, how to use those APIs, which API to use, and which using which parameters and those things. So that's it for this video. Now in the next video we are going to cover the another important peripheral and the part of the microcontroller of the S32K144, that would be our UART peripheral. So till then, stay safe, stay happy. For any doubts, for any queries, you can contact me on the reach out to me via the Gettobyte website or the Gettobyte mail, or mention them in the comment section. And don't forget to explore the Gettobyte website, where you can find number of things related to microcontroller coding and the technologies. So yes. So that's it for now, guys. Like the video and subscribe to the channel, and do share it among your friends, and press the bell icon to get notified with such videos as and when they are uploaded.